We see wind turbines with just 3 blades installed in wind farms, and some of them are relatively small. But wouldn't adding more blades to a turbine generate more energy? Or making it larger improve its efficiency? Today, I'll explain why wind turbines are the size they are and why their blades have only 3. Hello, engineering enthusiasts. Recently, we received an interesting comment here. I'd like to know why wind turbine blades are so thin and only have 3. If they were thicker or had more blades, wouldn't they generate more? I've always had this doubt. First, I'd like to thank Jânio for this great question, and if you have questions like this, leave them in the comments. Your questions help us create content tailored to your curiosities and establish a direct connection with you. Let's dive in. People have been harnessing wind power for thousands of years. Evidence of its early use dates back over 1,000 years in Persia. Over time, these machines have evolved from simple devices for grinding grain and pumping water to massive blades that generate enough energy to power entire cities. Traditional wind turbines come in various forms and designs, but all have converged on a consistent 3-blade design. But why only 3 blades? You can think of each blade like a wrench tightening a bolt. Increasing the wrench's length generates more torque, which drives rotation. Similarly, adding another wrench allows for even more force. This principle also applies to wind turbines. Naturally, one might think, why not add more blades or make them longer? The largest wind turbine to date is the Mingyang Smart Energy, with a total diameter of 260 meters. It features 3 blades, each 123 meters long. Despite being made of carbon fiber, each blade weighs approximately 54 tons. To give you an idea, the blade tips can reach speeds close to 70% of the speed of sound. But why not manufacture turbines with more or fewer blades? Let's compare the standard 3-blade design to 2-blade and 4-blade models, assuming they share the same blade design. In engineering, every project considers a cost-benefit relationship, aiming for an optimal balance over the turbine's life cycle. If we consider production costs over a turbine's lifespan, it takes time for the revenue generated by the turbine to cover production costs, after which it starts generating profit. Adding another blade increases production costs, reducing profitability. This eliminates the 4-blade design, where production costs outweigh benefits. Thus, we're left with 2- and 3-blade designs. Interestingly, 2-blade designs can match the performance of 3-blade ones. According to the Wind Energy Handbook, to achieve similar performance to a 3-blade turbine, a 2-blade turbine would require either a 50% increase in blade chord length or a 22.5% increase in rotational speed. In turbine blade design, the chord is the distance between the leading edge curve and the trailing edge. Increasing blade chord by 50% for each blade in a 2-blade turbine would result in the same total chord as adding a 3rd blade. Thus, there's little advantage to increasing chord length. Alternatively, increasing blade speed by 22.5% means the turbine spins faster. 2-blade turbines rotate faster in the same wind conditions due to reduced drag. However, faster rotation introduces challenges rather than benefits. Why? Faster rotation generates more vibration, increasing the need for stronger materials, raising costs. It also amplifies centripetal force, requiring reinforced connections and blades to withstand the stress. Finally, noise increases with speed, which is a significant issue for nearby residents. Considering these factors, the 3-blade design emerges as the optimal solution. It generates more energy at slower speeds than 2-blade designs and offers better cost efficiency than